The next one is this thing that's called an access control matrix. Access control matrix. And I'm deliberately going slow here, trying to make sure that I do my due diligence, because a lot of these models you'll start to see integrated into many of these other concepts that we're going to be getting through and doing. There's one, for instance, that is called the Graham-Denning model, and it is also referred to as the access control matrix model. Typically, for purposes of your exam, you'll see it organized in a way that, or asked in a way of the Graham-Denning model. And so what that does is it actually breaks it down into an access control matrix by having the the person that's going to be accessing it, so the user that's going to be accessing it, and then which object is going to be accessed accordingly. And somebody just put it in. Yep, you're absolutely right. That's exactly what it reminds me of as well. The change modify, the chmod within Linux. And so it's not as pretty when you go and look at it in Linux as a tab, but it is, typically if you do just a print on what the access controls are, it'll tell you, what that is, what those values are for that, the subjects or the objects. And so that's what is considered an access control list. And so each one of these specifically would be, this whole thing would be a matrix, but one specific here. So like this one right here, object 2, would be an ACL, or an access control list. And that tells us the column of the actions that the subject can perform on an object. And so that is the easiest way that I typically remember this. And so the Graham-Denning model typically will show how subjects and objects should be created and deleted, but also who can access and address assigning specific access rights to those subjects. I was first starting to prepare for taking this exam. I started to learn about all of these models and, the theory behind it. And, you had all these different peoples with different names, all these experts in access control and, all these, you learn about cryptography, they got all these people's names. So a much naive younger man, I remember the person that I was studying with, she said, I'm having trouble really understanding what this Take grant model is. And at the time I was just like, huh? She's like, yeah, these two people, Mr. Take and Mr. Grant, got together and they came up with this model. And I was trying to think of a way to refute it, but at first I was just like, how do you even respond to that? But no, it's not Mr. Take and Ulysses S. Grant here, right? This is the take grant. So you take stuff away or you grant permissions to it. And so how rights or our permissions are passed between users and computers, or subjects and objects. And so we can grant rights either between one subject and an object, or we can have a subject take rights from other subjects. There's oftentimes different rules that are associated with this take grant model, and hopefully you see this on the exam and you get a big grin and you think of me as you're laughing all the way to the the promised land with a pass on this. So the take rule allows a subject to take rights over an object. The grant rule allows that user to grant rights over that object. The create rule allows the subject to create new rights, and the subject allows the remove rights that it has. So oftentimes in programming, I typically call this the CRUD. What does that stand for? The CRUD. Is that the new variant of the flu that's going around? So whenever we're programming, in any type of programming, the hardest thing to learn as you're going through and starting to learn this stuff is, in programming I'm talking about, the hardest thing to learn is how to make the connection string to whatever you want to connect to. And it can be a tactical system, it can be a web server, it can be, a compiled system that, whatever the connection string is. That's one of the hardest things to learn. And then how are you going to be able to provision, deprovision it using the CRUD? So create, read, update, delete. And so the take grant model does just that. So I was teaching a course a little while ago, and I had somebody in the crowd who was weird security professional, and I started talking about the Bell LaPadula model, and he let me finish what I was talking about, and then he interrupted. He said, I've actually met Mr. LaPadula before. And so ever since then, I don't call it the LaPadula, I call it the LaPadula. So it's Bell LaPadula. These are the people that first came up with this model, and it was the first mathematical model that gave us the idea of a multi-level security and really defined the concept of these two guys, Bell and LaPadula, came up with a way to really qualify the secure state, the quote-unquote secure state, and give access accordingly. It ensures that the information flow in a manner that doesn't violate any system policy. And the primary thing here, the primary thing to remember is this right here. It is a confidentiality model. Confidentiality. So the Bell LaPadula is a confidentiality model. It does not address the integrity or the availability of anything that's in there. It tells us, based off of the way that information is flowing, what do we need to do in order to do that. And so here's an example of that in the Bell LaPadula. There's three different properties here. Three different properties. There is the simple security property, where the subject cannot read data within an object that resides at a higher security level, which basically means no read up, which you see in the top right of the screen. So users cannot read data that's at a higher security level. Remember, confidentiality, right? So if something's top secret and you only have unclassified access, you're not going to have access to classified. Then there's this thing that's called the star property, star security property, and that is the no write down. So a subject cannot write to an object at a lower security level. So it's no write down. So if you have secret data, you can't publish any content to somebody that has a lower level of classification as you. And so no write down. So there's no read up, there's no write down. And then there's this other thing that's called the discretionary security property, where system would use an access control matrix that we just saw to enforce discretionary access control. And that word, discretionary access control, means that depending on what the administrator of the system or the user of the system thinks is the right thing to do, it's at their discretion to give them access. And so basically that's a system override, right? Like if these are enforced for confidentiality purposes and we need to read somebody on to something, maybe they're on the Tiger team and we need to get them up to speed super quick, but they don't have the necessary clearance, boom, we're going to use our discretion. I'm going to get the colonel to get me the get a jail free card for giving them access, and boom, we're going to grant them access as soon as possible. And so that's the discretionary security policy. And so that is the Bell-LaPadula model. Another one here is this thing that's called the BIBA model. So the BIBA model. And this is a one that focuses on integrity. So not confidentiality, right? So if you're taking your copious notes, which I'm sure that you are, it's a set of controls that has different rules that are used to ensure data integrity. And so, when this was developed, it knew that there was a shortcoming with the Bell-LaPadula model, that it only addressed confidentiality. And so the BIBA model really came into play to say, how do we, here's a model that allows us to not deal with confidentiality. We deal with consistency. We deal with unauthorized modification. We prevent modification from things that we don't want people to have. The way that we remember this, if I say the beaver, but the way that we typically will remember this, or sometimes people come up with other ways, is BIBA Las Vegas. And so Las Vegas, what stays in Vegas happens in Vegas stays in Vegas. You can end up looking at it from a perspective of there's no integrity if it happens in Vegas. And so the BIBA model enforces integrity. So just to kind of give you a way that some people try to remember it. I'm not saying that's the way that you have to, but things that have worked for people in the past you might be interested in. So consider that whenever you're studying. Here's an example of it. There's two different properties in this particular case that are meaningful here that you may want to take a look at. Have you ever heard of, it's a play on words, it's the Elvis Presley song, Viva Las Vegas. So it's a play on words, it's like, Viva Las Vegas. Maybe I should play a little Elvis Presley here at 1:12 in the afternoon Central Time. No, but that's typically what people think of is, trying to help to remember. So let's look at these different properties right here. Simple integrity property and strong integrity property. Again, BIBA is focused on integrity only. Remember, that's what we were saying earlier. The simple integrity model is that a subject cannot read data at a lower integrity, which means no read down. No read down. The star integrity axiom, on the other hand, is no write up, right? So we have no read down and no write up. Why in the heck in an integrity model would we not want people to write down, or I'm sorry, why would we not want them to write up or read down? So again, this would be the way information is flowing, right? Yeah, can't create more confidential. Good. And so if we're just comparing apples to oranges here, right? Because they sound very similar, but one is specifically for confidentiality, the other one is for integrity. So let's just take a look at these two heavyweight, pound for pound, putting the tail of the tape next to each other, right? We have the Bell-LaPadula and the BIBA models. Both are for information flow, and we already went through and put some context next to the information flow model, right? They're mostly concerned with the information flowing from one level of classification to another level of classification, okay? So in that sense, they're the same. The Bell LaPadula uses levels to provide data confidentiality. The BIBA uses it for integrity levels to provide data integrity. And so for your exam here, you should know the rules of the Bell LaPadula and the rules of the BIBA. They sound very similar. Both have simple and both have star in them, and they deliberately did that. One writes one way, one reads another way. A tip that typically people say that they remember is if the word is simple is used, it's about reading. If the rule is a star or an asterisk, it's about writing, okay? Reading is simple, a star or an asterisk is writing. So now you just need to remember the reading and writing directions per the models. You can thank me later. So another topic for distinction is this thing that's called the state machine model. And you may have heard of this before. And if you haven't, that's okay. But basically, what this does is it gives us a snapshot of a system at any given time. And it's not like a virtual machine snapshot. This would be more of what is the status of all transactions as it's come across, and giving the ability for somebody to go in and quickly know what's going on within this particular model. And so the state machine model typically will try to dictate what a system should start up securely, how to carry out those secure state transactions, and if there is a failure, to fail secure or fail securely. And what that means is that if the system encounters something that it deems unsafe, it should change to a more of a secure state to kind of automatically preserve the integrity of it, or self-preserve itself and protect itself. So it's almost like a fail-safe in a way that allows it to start up securely, carry out secure operations, and then if there is something that's goofy that happens, it fails safe. And because of that, it's considered a secure state. And if you can make this happen. And so there's just a simple diagram down here at the bottom that kind of walks through that. If there are critical errors, it starts over from scratch. And this can be either really complicated or it can be quite simple. So think about that as you're going out and being awesome. This Clark-Wilson model was developed, I think, after BIBA. And it started to take some different approaches to ways to protect the integrity of information. So this one focuses on users, these things that are called transposition or transformation procedures, constrained data items, unconstrained data items, and then integrity verification procedures. And so again, it looks to try to protect the integrity of information as it flows to and from the system. They come up with what they call a well-formed transaction. I'm going to put that on here because that's one of the things that I have in my notes that is important for you guys to write down. If things happen the way that they're supposed to happen with this Clark-Wilson, we have what's called a well-formed transaction. And so this well-formed transaction can only happen if the integrity of the data is kept in check by different transformation procedures that happen to the data as it's collected. We have the integrity verification, so we look at whether or not the data is valid before we actually have a transaction with the data set. And so in order for us to do that with this particular model, it could look something like this. And in this particular case, again, kind of trying to keep it, you have the data over on the left-hand side with classification levels. And then in the middle, you have some sort of, let's just say a web GUI, and then, a user over on the right-hand side. The distinctive feature is focusing on the separation of duties in well-formed transactions. And so with these well-formed transactions, you go through a series of operations that really transforms the data items from a consistent state to another consistent state. And when I say that word, consistent state, it's one where the data is reliable, so it has integrity. And the consistency or the integrity of that data is the job of that transformation procedure. And so let me give you an example. Let's say that transformation procedure that I was just talking about on the previous slide comes into play. Let me pull that back up. This transformation procedure, it actually will take that data that was previously put in by somebody, and it will transform it in a way that is needed for the data set that it's about to go in. And so what the heck does any of that mean that I just said? Well, let's say that, I'm just going to give a silly example. Let's say that you give somebody over here on a web form. So somebody's filling out a web form, and when they're filling out this web form, they have, where am I at? I'm right here. Okay. They have the opportunity to input some data. And so, for instance, if they put in their social over here, let's say they put it in that format on the web form, what the transformation procedure might do is, this is the data that is collected by the end user right over here on that I just put into there. The integrity verification procedure, I'll take that data, just give me a second here. So the transformation procedure might be right here. And then one final check over here might be the IVP. And so what it might do is it says, yo, hey, I got your data, the transformation procedure, but you know what? We need dashes in there. So I'm going to transform the data that you gave me, and I'm going to put it into a format that is going to keep the integrity consistent within my data set. And then over here, this integrity verification procedure, look at input validation, as well as probably run some sort of regex on it. So it'll look at a regular expression and make sure that it's got the proper formatting. And it does this with basically a repeat and repeat right here, right? So we have the transformation procedure that transforms and rolls out the data. And then over here, it basically says, hey, yo, I trust you, but I'm going to verify. And when I trust you, but I'm going to verify, before I put the data into my data sets over here, I'm going to transform it first to keep the integrity. Then we're going to make sure we trust you, but verify before we put it into the system. And again, these are all models that we are hopefully going to be able to, at a super high level, the 5 to 7 words, right? We're going to be able to go through and, at a high level, answer test questions about this. And so what this one is basically it builds on that last one of a state machine and allows us to look at how the data flows. What are the IOs with the system? And so, in that state system, going back to the trusted computing base, all those protection mechanisms within the system, hardware, software, firmware, whatever, those are all controlled with that trusted computing base. Well, the information flow looks at things as they're going in and out of the system and determines whether or not things are allowed to go out or things are allowed to come in. And either way, it could filter or prevent unauthorized information flow. And so the idea of it is to almost like a service or a process that's running that allows the controlling of information to and from the system. And so that's why we call it the information flow. And so it works on, again, sticking at a high level here. This only works when you are in a secure state, right? So if you're not running in a secure state, if your operating system or again firmware, hardware, whatever we're dealing with doesn't work in a secure state, then this isn't going to be something that's tangibly going to be able for you to actually achieve. But if you are able to, then what does it look like? Well, there would be almost like a the constraints of the information flow. So if we put a label on it of restricted or sensitive or limited, and somebody has access only in a limited capacity, if they're trying to access sensitive information, they would not be allowed. If they're trying to access restricted information, they would not be allowed. So based off of what level of access they have, the information could flow freely between the the trusted computing base, the security application, and the user. And so that's typically how the information flow model will work. All right, so now we talk about this one, which is the non-interference model. So with multi-level security processes or principles, you can express them in a number of different ways. One of them is non-interference. And so this idea was implemented really, I think, to ensure that any action that takes place at a higher security level doesn't affect or interfere with actions that take place at a lower security level. And so it doesn't look at the flow of information that we were just talking about. This looks at what a user or subject knows about the state of the system. And so something that's at a higher security level performs an action. The change to the status or the state of that system at a lower level could raise a flag and set an alarm off. And in this particular model, it's made up of rules where certain subjects can't pass data to other subjects through any type of a covert channel. And so this is the first time that we're using that word, the covert channel. And so let me just put it into the text here of the chat. A covert channel, just in case you haven't watched a spy movie in a little while, is a way for an entity to receive information in an unauthorized manner. And so the covert channel just sounds James Bond. A couple more here that we're going to go through and do with the security models. And again, I'm recording all this so you can come back and look at it on your own accord, because I know you guys are definitely interested in hearing my voice for another 40 hours. So this one is actually called the Chinese wall model, the Chinese wall model. And it's the Brewer-Nash. Sometimes I refer this to as well as the Jesus take the wheel model, the Carrie Underwood song, where you just throw it up and You say, hey, my hands are off. Jesus, take the wheel. I'm throwing it over the fence, because typically there is some sort of conflict of interest. Think about a time in your life where there's been a big decision that needs to be made, and maybe you were working for a nonprofit, or wherever you were at, the decision needed to be made. And when it came down to it, what happened? Well, essentially, you have to get to a place where you feel confident that if you're too close to it, you can just say, hey, I know this person over here. It just doesn't make me feel good to or feel confident that I'm going to be able to objectively or have unbiased with the decision here. So I'm going to recuse myself. And so that's the scenario where you throw it over the Chinese wall, you throw it over the wall to somebody else to avoid a conflict of interest. And so that is the Brewer-Nash. And that Brewer-Nash is, it definitely comes in handy, right? And so in context of, the information flow, it states that a subject can write to an object if and only if that subject cannot read another object that is in a different data set. And it was created primarily to try to provide some sort of access control to information that can change dynamically. It's designed to try to mitigate the risk of any issues happening where any previous action could dynamically taint information on an action that's about to happen. So that is the Brewer-Nash model. And the last one here is this Graham-Denning model. Remember, with all these models, they're not very specific in nature. And that's what makes it a lot more difficult, is because they're not specific and more abstract, you're just like, what in the hell is this person talking about? But really, yeah, absolutely. Some of these models are super extreme use cases. But some of them you can absolutely apply them to things that we do, right? And so each individual vendor that's out there or organization has to make a decision on how they're going to actually meet the rules that are outlined in whatever model they choose. We're not going to use all of these different models, but if you are looking for the Bell LaPadula, and maybe you are also wanting to implement the BIPA, you may need to look at it in a way that is interesting and convenient for you, because one provides confidentiality, the other one provides integrity. But the Graham-Denning, on the other hand, that we see up here, addresses some of the issues and defines the different baseline level of rights that are needed for operands or commands that a user can have over an object. So what's a subject able to execute on an object? And that's what happens here. So different users have different permissions within different applications. And so these 8 protection rights, they're called, are rules of how these different functionalities should actually take place. Again, the users executing different tasks within an object. So there's securely create an object, securely create a subject, delete an object, delete a subject, read access right, grant access right, delete access right, transfer access right. Yes. No, it is. It's the same. These functionalities are super important whenever you're talking about a secure system, and they're actually critical. And so exactly what we were talking about before, right? That's how if you recall, that's how I started it off with the Graham-Denning model, is all of this collectively is the access control matrix. And then one specific column here would be the access control list. And so it kind of tries to bring it all together in a way that's a secure manner where hopefully it can't be compromised by an attacker.